day of our virtual workshop. In this section, at least the first half of it, we'll be talking about experimental frameworks, and in the second half, we will be moving on to workflow management systems. So our first talk will be done by Attila, as he'll give a summary on how various experimental frameworks are attempting to handle the heterogeneous computing needs that we see in our future. Attila, do you want to go ahead?
Yes, let me do that. So as Chris said, the idea with this first part was that that we would give really just a very broad overview of what different experiments are doing right now to make some take some advantage of accelerators. And keep in mind, while I'm trying to just give some very broad stroke overview, that this is really a very very quickly developing field, and I do think that we are still sort of at the beginnings of how we, of understanding how we want to do this. But with that in mind, just because I thought that maybe not everybody is too experienced with writing accelerated code in general, I just wanted to point out some of the basics that these days, pretty much whatever accelerator you use, whatever type of GPU or even non-GPU you want to use, you usually write programs for it in the same way. All of these accelerators always assume that you run your main application on a traditional CPU. And this sort of came up as a question already yesterday, but basically everything that we do always has to start from a CPU, where you run a sort of a traditional application, which in the simplest setup just prepares some data that you want to do some calculation on. It makes sure that all of that data is copied to your device, to your GPU or whatever else. And then it also has to spend a little bit of time setting up the calculation on the device. And all of these steps may take some not completely negligible amount of CPU cycles. Now, when the execution starts on the device, in the simplest setup, usually the application on the CPU just sits down waiting. And until the calculation is running on the accelerator, it is just waiting for the calculation to be finished. And once that happens, the execution flow goes back to the CPU. It usually copies back at least some amount of data from the device to the host, and then the execution moves on. As you can see, in general, in a very naive setup, you might have a fair amount of idle cycles on both the GPU and the CPU. And how much you try to avoid this, and in the end, it really depends on your use case. And this is where some of the discussion will be on the different methods. So as I said, in just a very broad stroke setup, we sort of see three different organizational setups for frameworks that exist right now and which can use accelerators. And these are even sort of tied, at least in our own minds, to different LHC experiments, because, well, this is what we've mostly been focusing on here. So what Alice is doing is that their offline framework was based around the idea of running multiple processes which interchange data with each other, even share some data in memory, and without using any real multi-threading, separate processes do the individual parts of execution. There is also and I'll say a few words in a second about the upsides and downsides of that. Now, there is the LHCb method that you have probably heard about what they are doing with their HLT setup with Alan, where they are focusing really on making use of the accelerators as efficiently as possible with pretty much zero CPU usage. And then the third one is sort of a hybrid setup where we only use a single process. So this is what CMS is actively doing and Atlas is trying to do, where we would have a single multi-threaded process which tries to offload some of its calculations to GPU in some efficient way. Now, as I said, for the separate process setup, this is working pretty well for Alice. As I said already, the idea is that an accelerated process can just offload calculations to an accelerator. These days, mostly with CUDA, just using the native APIs of CUDA. And generally, the code does not have to be super complicated for that, because since the process is just doing this one thing, it can, in principle, execute the accelerated calculation exactly as I've shown 2 slides ago. Now, some pros and cons to this, at least in the very naive view that I see this. As I said, I do think that programming-wise, it simplifies things quite a bit. That they can use the synchronous API for offloading. They don't have to worry too much about asynchronously running calculations. But from what I've seen, dynamic load balancing can be a bit of an issue here, because with multiple processes, if you set up the number of processes that you use incorrectly, unless your framework is very smart in launching or stopping processes, you might not be taking full advantage of your hardware. Now, the other thing, as I mentioned, what LHCb is doing is that they wrote a framework from scratch whose main purpose is to run calculations on accelerators. And the whole framework is designed around this. This does, well, there are some details listed here of how they had to come up with their own memory management, which actually in other frameworks pops up as well. How configuration has to be a bit more static compared to some of the very dynamic configurations of the other frameworks. But the upside of this setup is that since everything is written from scratch, the whole point is to be as efficient on the GPU as possible. And just as I point out on the next slide, so with this setup, since the whole design is based around accelerator APIs, you can expect to get the most out of your hardware. Some of the cons might be that since you're really specifically writing for specific hardware, if you want to run the same code without that hardware present, either you have to come up with your own portability solution, similar to what we've been discussing yesterday, or you can only run these things on the accelerator. Plus, anybody who's done any serious amount of accelerator programming knows if you have to write your code from the ground up specifically for accelerator hardware, the learning curve can be just a little bit more steep. than writing basic C++ code. And this brings us to sort of the slightly perhaps more complicated solution that CMS and Atlas are trying to use. Well, CMS is actually using it. Atlas is just trying it. Where in both of the experiments, we are using multi-threading to distribute our calculations on a set number of hardware threads on the CPU, which just in a very naive view, in the Atlas lingo, you would run algorithms that would process data from different events according to some scheduler on these different TPP threads. Now you're trying to teach some of these algorithms how they should be running their calculations on an accelerator. And the very naive view of this, and Matthew will talk a lot more about this later on, is that we sort of have to rely on the asynchronous APIs of these accelerators, because we can, in general, not afford to have the CPU threads sitting and waiting until the accelerated calculation is running. Mostly because some of the calculations that we are trying to offload do not provide like orders and orders of magnitude of speed up, as in some of the other cases. So we have to make sure that our CPU efficiency stays as high as possible. Now it's worth mentioning, and this I really just wanted to bring up quickly, that there are multiple ways of achieving this, of making sure that the CPU stays busy on multiple threads. One way is to bake this information, this knowledge into the actual scheduler. Or you can also, if you don't want to fundamentally rewrite your multi-threaded scheduler, you can still do some clever tricks with TBB and some oversubscribed STD threads. But in the end, it depends on what type of complexity you want to have in your framework. Now, just to quickly mention some of the very naive pros and cons here as well. Usually, one of the pros here could be that you can set up your scheduler, or you can hope to set up your scheduler in such a setup such that it could offload calculations with the least amount of CPU overhead. So that even if your accelerated calculations do not provide a huge speed up compared to how they would run on a CPU, overall, you would still get a throughput increase. Well, some of the cons are that the implementation of such a framework is also not simple. Having developers work with the asynchronous APIs of the accelerators can be a bit more challenging, especially for beginner developers. Now, and really just to bring all of this to a summary, and then to open a little bit of discussion on where we are with all of this and where HSF might be heading. I would argue that choosing how you want to run or how you want to design your accelerator-aware framework is really a many-dimensional problem. It really depends on let's say, first of all, how easy it is to accelerate your calculations, how vectorizable it is. Of course, the more vectorizable your calculation is, the easier time you will have with an accelerator. Depends on how much memory your application is using already, whether you can afford to not do any CPU multi-threading in the whole setup. And it also depends on how portable your code has to be. And yeah, at the moment, we really see experiments being everywhere on this spectrum, basically. And this is what what we will try to further discuss in our working group meetings as well. So okay, that's what I wanted to just give as an introduction. Hopefully.
Thank you, Attila. So we will be taking questions coming off of the live notes. If people can't reach that, I will attempt to look at any hands that are up as well. But we'll start from the live notes. So Attila, can you stop sharing and we'll switch over to Kyle on the live notes?
Okay, so we have a multi-part question from Gordon Watts regarding slide 7. The learning curve is steep, and this was regarding the primary process acceleration for LHCb. And the question is, can it be avoided? And will there, and more in the line of what does this mean for like a starting graduate student? Will it always be a specialized type of thing, or is there something that somebody just starting off will be able to do?
So yeah, if I can answer, so or I'll try to at least. So as Gordon points out, well, this is what Charles was talking about yesterday, and the question sort of already came up there, that there is a worry that while writing code through these portability solutions can make our life quite a bit easier, we don't actually know exactly how less performant of accelerated code we end up with when we write code through such languages. For LHCb, since their main goal was to be as efficient with on the GPUs as possible, because they only have so much money to spend on their HLT. Using some clever portability solutions, or at least the ones that are on the market at the moment, I think that's a pretty tricky thing to do. And just to mention that every time that I talked with NVIDIA developers so far, the comment was that they really don't see how portable solutions can give access to the full performance of their hardware. Now, in the end, I hope that this will not be an issue, because as we all know, we don't take advantage of the full performance of our CPUs either, and we can sort of survive with that. But yeah, in an HLT environment, you might have to bite the bullet and yeah, teach developers how to code like this in a more hardware close setup.
Okay, thanks, Attila. Paolo asks a question that is somewhat similar in that perhaps it makes sense that we target the simplest possible setup from the frame point of view, and then maybe consider some more complex scheduling schemes to get that last bit of GPU performance. What is your opinion on that?
Well, good question. Here, yeah, we keep saying, and I very much agree, that as long as we manage to come up with some brilliant new ways of let's say, doing tracking in CMS and Atlas, one that that uses vectorization in a much smarter way than what we do now, then most of our problems would be solved. So yeah, there is a point here that I think it's very valuable to think about algorithms at the moment. But maybe if you're a bit less optimistic and think that we might not be able to find those really good algorithms anytime soon, then, well, working on the scheduling, I think it's a bit more than just a 10% thing at the moment. It could be like a factor of 2. But yeah, I think these are sort of equally important at the moment. You can make the argument that working on algorithms might be a bit more urgent.
Okay, thank you. There's also a comment from Charles that synchronous offloading shouldn't be off the table. NVIDIA has made significant progress in its drivers since the beginning of the year to allow offloading the threads on the CPU to do other work while the GPU is waiting. So, and by the offloading thread, that is the hardware thread that's being referred to.
So that's true. At the same time, well, it might be a bit more of a technicality, but one of the things which NVIDIA at least is not great with just yet is that some of their APIs cannot be used at the same time from multiple threads. So even if you don't want to use their asynchronous API, you still have to do something to serialize how you launch your calculations or do some things like this. So just starting STD threads by itself, it sort of works, but you're running into a lot of mutexes. Well, as long as you're actually trying to run many calculations at the same time. So yeah, it's true that synchronous waiting for the end of the calculation is not completely off the table, but you still have to do at least some amount of smart scheduling to make sure that certain calls are just done one by one.
Okay, thank you, Attila. Looks like there are no more questions so far, so I'll stop.
So if somebody on the participant wants to just raise their hand and ask a question, they can just raise their hand. I'll give you a moment to make a decision, else we'll switch over to oh, we have one. So go ahead, Andrea.
Hi, this is Andrea. I think one of the first questions was also about how easy it's going to be for people to use GPU frameworks or portability frameworks. The very limited so far experience we had with 3-4 people that had joined CMS to work on that seems to say that using CUDA or using Alpaca, for example, is not particularly more complicated than writing CMSSW code in general. Now, this may mean that CMSSW is an overly complicated beast by itself, and probably we can agree on that. But that we have to use anyway, so adding CUDA doesn't seem to hinder too much people from contributing. What is difficult is figuring out the patterns that you want to suggest people use, like how to use memory efficiently, how to use scheduling efficiently. But once you manage to do that, implementing the individual algorithms seems reasonably doable.
Yeah, I can only agree with this, that this is sort of where things are going, that with these types of hardware becoming more and more prevalent, we won't be able to avoid at least learning the basics of how to write this sort of code. And I think Andrea was very right in that. Well, once you know how to write modules in CMSSW or algorithms in Athena, and you know sort of you can grasp the setup of the framework itself. Yeah, just understanding how offloading calculations is done, like on some basic theoretical level. Yeah, I agree. That's not such a big step at that point.
Okay, I don't see any more raised hands. So if that's the case, thank you. Thank you, Attila. Oh, Charles, you had something? Oh, there you are, Charles. Go ahead.
I just wanted to say one thing. I think that for people who are, the whole question about how hard is it to write the code, I think it really depends where you come in to the process on the curve. I mean, if you go in right now, I think there's a big difference to how hard it will be if you go into or start working in 3 or 4 years, because there's still a lot of work which needs to be done that's kind of really at the more, expert fundamental framework level. Things like, how do we need to massage our EDM to make it offloadable or to make it more friendly to GPUs? I think that in a few years we will have addressed all these issues. And so for someone who is a new graduate student, or someone who wants to port an existing algorithm or some calculation, I think that all the hard work will really have been done, and then it will be relatively easy. At this point, though, there is still a lot of work to understand what needs to be modified in our code, and it's pretty broad ranging as to what all the different aspects. I don't think we know what all the different aspects are right now, especially in a big complicated framework like CMSSW or Atlas's Athena. So I think that as time goes by, things will get much easier.
Okay, so we have one more hand. Liz, do you want to ask something?
Can you hear me?
Yes. Okay,
great. Yeah, so it sounds like in the surveying that this working group originally did when I was more involved, we had a little trouble getting a hold of Alice and LHCb, and you guys have made up for that. One of the things I was wondering is, they've gone in these different directions because of the inherent problem domain, where Alice has these really big events and LHCb has really tiny events compared to CMS and Atlas. But I wonder if you guys know, is there can you make that statement a little bit more quantitative, and how it might inform other experiments where they fall on this domain, and if you think that that's the right metric to choose which direction to go in?
It's a very good question. Very naive at this point. I could only say that, well, we've all seen what came out of the GeantV exercise, and I sort of get, well, there must be some point on, let's say, the event size curve on which, above a certain event size, it can be efficient to just offload all the calculations of the event type on just one event at a time, and then get it back and make efficient use of it. At one point, of course, this becomes inefficient, and you have to start grouping your events. But I would argue that once you get to that point, I think the approach that LHCb is doing is what has to be done, because what we saw from GeantV is that there can be such a large overhead with grouping events and then taking the event data apart afterwards to once again handle those things event by event. So I think at least this point we only know that, yeah, there is definitely some point at which you have to start writing code similar to what Alan is doing in LHCb. What that point may be, very good question. I think in CMS and Atlas we are hoping to God that we don't have to do this, because as I said, that would put up an additional overhead in all of our offloading.
All right. Thanks everyone for asking questions.